Okay, welcome everybody in person and on Zoom to our very first Sensorimotor AI Journal Club for researchers who value scientific understanding in addition to SOTA. So we like both. And we're going to do this every first Thursday of every month. And there's going to be breakfast, BWW or any other building, Berkeley plus Zoom. And this first meeting, we're going to discuss this paper from Jones et al., Bayesian online natural gradient, or BONG. And this meeting has the following outline. We're going to start with, so because this is the first meeting, we have a few slides just to introduce what do we want to accomplish. That's what is our mission and some logistics stuff. And after that, we're going to introduce inference and then online inference, and then motivate why should we care about this, but why is it an interesting problem before going to the actual paper's discussion. And then after that, in part 3, we're going to discuss the actual paper with some important background about VLR. If you were on Slack, you might have been following that, Kevin Murphy, the last author of BONG, joined us, and he shared that BONG is a very dense paper that builds on VLR. We're going to make sure that we introduce VLR properly so we can understand BONG. And finally, the Q&A that will not be recorded. This is us. So I'm Hadi. I'm a postdoc with Jake, who is here. And I'm part of Redwood Center and also Vision Science. I did my PhD in physics and then switched to computational neuroscience. And I'm here doing brain-inspired AI. Go ahead.
I'm Kaylene. I'm a final year PhD student, actually about to graduate in a week at the Kalman Lab here at Berkeley. So I'm in technically electrical engineering, but I work on representation learning for robotics. But I also have a lot of sort of connections with neuroscience and a little bit of background in neuroscience as well.
Congrats. All right. So Tommaso, unfortunately, couldn't join us. He's a research scientist at Versus AI. He couldn't join us because he's European and he's on their usual 3 months vacations. But I'm kidding, it's just 2 months. All right. And Eli, do you want to go next?
Yeah, hi, I'm Eli. I'm a postdoc with Andre Bastos at Vanderbilt, working in monkey and mouse electrophysiology. And yes, in my spare time, neuro AI.
I thought that's your main thing. Okay.
I'd like it to be, but it's not.
Yeah, it should be because that's the most. Anyway, right. Okay, so that's us. Here's a little bit about you. So 140 people signed up on our form, which is way beyond our expectations. So that's awesome. Thank you guys. And out of 140, 110 joined our Slack. So it's pretty amazing. And this is the kind of the pie chart of you. Mostly you are graduate students, 53%, followed by postdocs at roughly 17%, and then an equal portion of professors and industry independent people, and then we have 8% of ambitious, curious undergrads who joined us. And mostly you're on Zoom, so we're going to make sure that the meetings have they work for all of us. And this is your background and interest. So mostly, most of you are from AI, ML background, and there's the second largest group is from neuroscience, and then physics is the third. But the thing that is interesting is that most people clicked on more than one option, which means this is an interdisciplinary group. You have to, that's kind of our strength, and we want to play to that strength. All right, so let me explain why we even did this. In the advertisement, we said this is a group for people who value scientific understanding. But what does that mean? Let me try to offer you the definition of that. So if you want to understand something, like in this case, principles of intelligence, you have to provide a scientific explanation for intelligent behavior, which is the phenomenon to be explained. But again, another word, what is explanation? Here, I'm going to just borrow from Eugene Wigner, because I'm a physicist and I like his abstract way of thinking. He says, explanation is the establishment of a few simple principles which describe the properties of what is to be explained. If we understand something, its behavior should not produce any surprises for us. So this sounds like, a very abstract kind of like theoretical understanding, but I recognize that this might not be feasible for complex systems like studying the brain or intelligence. But anyway, this is what motivates us. When we read papers, we want to abstract away the core principles and insights that paper offers us and then carry those with us. We're not interested in the nitty-gritty details. Those you can study those with like your favorite LLM. You want to understand the principles. And yeah, we are an interdisciplinary group of people. And for example, if you want to understand intelligence, you have to draw from all these different disciplines and domains. And I'm not, we're not really interested in the actual skills or whatever domain knowledge here. I mean, that's important too, definitely. But what we want to highlight here is people's way of thinking, and the tastes and the biases that these different groups of people bring to the table. And this is especially important at the age of, in the age of LLMs, where, you can actually just have any technical detail you want to understand. You can just ask your favorite LLM and just have a conversation about it, you understand it. But these LLMs are not good at asking questions. So that's what humans do best. Like we have our own tastes. We ask some, interesting questions that it is kind of depends on our biases and backgrounds. For example, you might actually think that like physics, mathematics, philosophy type of people, they like abstraction. They don't care about details. They want to just find abstract, unifying, parsimonious theories of everything that explains many phenomena. In contrast, you might have a neuroscientist who's interested in concrete details and they're interested in, I'm going to measure all the details that I can possibly measure about this brain that produces intelligent behavior. And these are kind of contradictory at first, but then when you get these people together and make them collaborate, amazing things happen. It's not easy. And speaking from like personal experience, I started from physics, and I just like when I went to neuroscience, I was like, what is this mess? Like it's just a big pile of facts, right? But then you just grind and you just try to appreciate this interdisciplinary thing, and just if you put effort, you can actually make it work. And again, finally, in the last group, we have the pragmatic engineers. If you take a physicist who's like, oh, we have this theory of everything, and present it to an engineer, they might be like, okay, but it depends, right? This is, in practice, does it work? And I'm honestly, I personally am starting to really appreciate this engineer mindset, because if you want to actually make something work, beautiful theories are just, maybe like 30% of the way. Like 70% is just like hacks. Put together some hacks, make it work. So, okay, in conclusion, we want to bring these people together and in our journal club and learn from each other and like openly discuss our ideas and our ways of thinking so we can, learn from each other. That's the point. And yeah, just to drive this point home, why interdisciplinary thinking is interesting and impactful, there's all sorts of examples that we're all familiar with. Like the CNNs were invented when people like Fukushima and LeCun were inspired by the findings of Hubel and Wiesel on how the primate visual cortex processes visual scenes. Another example is just RL, and diffusion is a very interesting example. The stories that Yasha was a PhD student at the Redwood Center, and he was inspired by modeling the brain as a generative model and like bringing ideas from statistical mechanics, and then he ended up inventing diffusion just by being inspired from both the brain, but also mostly from physics. This one I learned recently. So did anybody go to this Agentic AI summit this Saturday? Okay. Yeah, it wasn't really, honestly, it wasn't really interesting because most of the talks felt like they were just like, the slides looked like some marketing person, like, some MBA person rather than a professor would put those slides. But there were some interesting moments. My favorite moment was Ed Shai, or Ed Shi, I don't know how to pronounce his last name, who's VP of Research at Google DeepMind, was just hanging out in the back patio and like talking to 20 of us, and he just like for 3 hours. And one of the interesting things he mentioned is that when they were inventing this chain of thought prompting idea, he was inspired by Jean Piaget's schemas. And Piaget is a psychologist from like 1920s and 30s. Schema basically is something like, looks like a prior in Bayesian inference, but whatever. And lastly, this paper that came out, Hierarchical Reasoning Model, that actually outperforms chain of thought prompting is also brain inspired. They cite a lot of neuroscience papers, and they outperform big models like Cloud and R1 with like a 25, 27 million parameter model. So all of these models or ideas came from marrying distinct disciplines. And here's another paper like you can read. It's a very interesting perspective piece from Martin Scheffer, who's an ecologist and a complexity scientist. He says, reading things unrelated to your research and hanging out with strangers in a campus pub should be considered part of the serious process of thinking. Because people who were distracted like that, they actually, found the next breakthroughs. So we want to do some of this stuff in our journal club, hopefully. And okay, speak of interdisciplinary. Another thing that we're very interested in is that we need diverse perspectives to be able to understand intelligence. Here's two contrasting views. The mainstream view is that you need only scale to make things work, which is actually great. I mean, this has given us awesome technology that we can use and improve our research and our lives. But in order to understand intelligence, you cannot just do that. We think you have to just study how the brain does it, because that's a good example of something that produces intelligence behavior. And brain is something that evolution created. It wasn't engineered. Another point here is that when you want to deploy things in the real world, that's a categorically different thing from deploying things on a web server that people can interact with through the web browser. If you want to deploy in the real world, it has to be like the algorithm has to be energy efficient, it has to generalize. And those are things that current mainstream scales, all you need AI kind of, usually suffers at. And we have a good example of organisms like humans who do that very well. So we can actually learn from the human brain and make progress there. So these are like my takes on this slide, but I know that we have even within our own, organizing team, we have diverse perspectives. So I'm going to let Kaylene and Eli also share their perspective on this.
Yeah, so I totally agree with everything you just said, but maybe one additional motivation to really care about this problem of how systems can work more efficiently or with principles that we actually understand is that as we have been increasingly deploying these autonomous systems in the real world, I think it's really important to actually care about safety and having a good understanding of how they will behave in many different situations, including those that they haven't actually been tested on, simply because you can't test in advance on every possible situation that you might need the system to behave safely in. And so I think building this deeper understanding of the principles that underlie intelligent behavior is really important from a practical perspective as well. Yeah.
Thanks. Eli, do you want to go next?
Yeah, I'm going to be Mr. Hot Take and say, I don't think that models we have right now really are all that intelligent. I don't think scale is all you need. Memorizing behaviors and then repeating them is not the same as actually constructing new behaviors de novo, or so to speak, as demands the situation. And to understand that, we really do have to go back to the brain.
Perfect. Yeah. So yeah, again, interdisciplinary, diverse perspectives, the brain. That's what we are interested in. Next up, okay, what do we hope to get out of this, right? First of all, we want to have lively discussions. Please interrupt at any point. That's a good thing. So if you interrupt more, that's a performance metric. Let's maximize that. Also, we want to avoid monotonic one-way flow of information from us presenters to everyone else. That's just going to totally avoid that. And again, question, comments, don't hold back. Just a reminder, this is being recorded. It's going to be on YouTube. And it's going to be, yeah, but if you want to invoke the fifth during this main recording, you can actually hold your comments to the final part if you wish. Okay. All right, so we want to also encourage you guys to volunteer to present. So for example, anything you're passionate about that is within the bounds of the group's overall interests, go for it. Could be a book, chapter or paper you want to read, or a paper you've already read and you're very familiar with it, and you can just present it. It's like great return on investment. And it's going to be on YouTube. There's a proof that you know that paper really well. So think about it. Or a tutorial or a method you find interesting, you use in your own research, and you think the group will benefit. Just volunteer to present that. Finally, if you have a paper or blog post that you think we should know about, totally. And the method to do this is just, we have this channel on our Slack, main underline paper nominations. Just put it there, like put your suggestion there with a very brief description. Okay, here's why I'm excited about this. Here's why the group should be excited about this. And we can all vote. Just a reminder that for next month's presentation, we have already selected BONG, the other Kevin Murphy paper. But after that, we're gonna just be more democratic about this. Okay. And this is our Slack group. Hopefully you guys have all read the README. It's basically all of the things we just talked about in text format. There's always going to be a current underline something channel. That is the current paper we're currently preparing and reading before the meeting. And then after this meeting, we're going to archive this channel. We're going to make another one. It's going to be current set 25 BONG. And then the meeting logistics is where we share Zoom links, whatever, YouTube, where the room is for in-person people. And then the nominations I just told you, and introduce yourselves. First of all, thank you for all of you guys who posted. That's great. That's great engagement. And if you haven't posted yet, please go ahead and share a little bit about yourselves. We just want to build a community. And networking jobs is for, just if you want to, like, if you have a job opening, or if you think there's a job opening people might find interesting, just put it there. Or, maybe like before a conference, we can organize some little socials. So that's for that kind of stuff. The random part is like anything that doesn't fit in the other things, like including memes. Go ahead and put them there. And then the resources, papers, tutorials, these are like whatever you think the group might find interesting that you just want to like drop a link. Oh, this paper is interesting. Just people can take a look. And another reminder is that we're going to discuss BONG. We're going to discuss BONG next. It stands for Bayesian Online Learning in Non-Stationary Environments. And the key for BONG is the non-stationary part, which is not what the authors explored in BONG. We're going to get to that. But I just want to mention, like, I don't know if you guys had this problem, but, whenever I wanted to get like kind of like quick look at the PDF of the paper, I would just search like BONG paper and it wouldn't show me. So the struggle was real. All right. One last.
You're going to show other pictures on the left there.
No, that's fine. Okay, so last thing, we want you to join us. Unfortunately, or fortunately, whatever, Kaylene is graduating and she's leaving. So we need someone to represent Bear on our team. I'm representing Redwood Center, and we need someone who's officially affiliated with Bear so that we could keep doing this. And the commitment is just really minimal. Like the main heavy lifting is done, it's up and running. And like, what you're gonna do is like help with organizing meetings, like order food, pick up food, or things like that, like, reserve a room, and then building access. Like some people don't have access to these buildings, like this one or BWW, just let people in, that's it. Benefits, it looks great on your CV. It's a leadership experience. You can say, I co-organized and led a journal club of 140 interdisciplinary scientists throughout the world, whatever. And importantly, you can help shape the discussion at the intersection of AI. You have a vote, you have influence in how we're going to take this forward. And if you're interested, just talk to us after this meeting or just DM on Slack. We'd love to hear from you. Okay. All right, so what we did was we're done with part one, and now we're going to go into the next part, which is now we're starting to actually get into the kind of the materials, like the scientific part of things. We're going to introduce inference and then why we should care about it. But before getting into online inference, which is the topic of BONG, let's actually start with this. What is inference? Let's understand inference. Well, it's your brain trying to guess the hidden causes behind what you observe. That's one way to define inference. So the brain receives sensory information like photons landing on your retinas, and the brain has to map those photon patterns into the state of the world. That's inference. The observations are photons and the hidden causes are just the state of the world. And this is best captured in this Helmholtz quotes. Actually, I didn't verify, I could never verify this. I don't know if it's actually true, but it's attributed to Helmholtz. But doesn't matter, it makes a lot of sense. It says, perception is our best guess as to what is in the world, given our current sensory evidence and our prior experience. So it is a combination of two distinct components. It's whatever you're receiving right now and whatever you've learned, your prior world knowledge. And just another, I'm going to do a little plug here. I have a blog post on this. Feel free to go check it out. And yeah, this is another perk of presenting. You get to plug your own stuff. Okay. And this idea in this sentence is in English. If you want to translate it into math, you can just formalize it as Bayesian inference, thanks to these guys, Bayes and Laplace. This is the posterior. Z are the causes. X are the observed images. The current sensory evidence is the likelihood, and prior experience is the prior distribution. And this is just a Bayes rule. And here's a little demonstration why Bayesian inference can be used to understand perception. How many of you have seen this illusion before? Wow, okay, most people. All right, the majority of the, that's awesome. Okay, so the illusion is that, you just see this and you imagine, you just like, oh wow, this guy must be a giant and this guy must be a real short person. But there's another explanation. The idea is that, first of all, this is person A, red here. Person B is green over here. And there are two equally plausible explanations for this sensory evidence, that the particular pattern of photons that your eyes receive in this image. One is that the room is actually veered like this, and this person is not short. He's just standing far away from you, so that's why he looks really short, because he's far. And person B is actually much closer to you. But the other explanation is that the room is actually rectangular, and the people are standing in equidistant to you, but one of them is really short. And because we have this prior expectation of, we only have seen rectangular rooms, we've never seen this weird room, right? We've never experienced that. We have this like overwhelming probability we put on this rectangular room prior, and that causes us to, in our posterior, to also favor that explanation. The key observation is that same sensory evidence, like these two distinct or different world setups, give you the same evidence, but because your prior is skewed in this direction, it's going to give you a skewed perception. And that can be beautifully modeled as Bayesian inference. And formally, you can just write out, Bayes rule like this. So this is your posterior. It's just likelihood times prior divided by the marginal. And the key observation here is that the marginal is hard to compute. This integral is difficult to compute, except in very simple cases, but like where everything is Gaussian or something. And it's also hard to estimate, usually in like complicated high-dimensional distributions. Therefore, we have to approximate this. We don't really have access to this posterior over here. And what we do is we introduce this new distribution called approximate posterior or variational posterior with variational parameters lambda. And we want to bring it closer to the true posterior, which we measure using the Kullback-Leibler divergence or the KL divergence. So we have this posterior, approximate posterior on here, and then the true, or let's say optimal posterior here. We don't have access to this guy, but because of the properties of the KL divergence, if Q and P are identical, this function gives you 0. But if Q is different from P in any way, it's going to be a positive number. So it's non-negative and only 0 when Q coincides with P. Therefore, it's not exactly a distance metric, but it's kind of a divergence. So you can actually minimize this to have better posteriors. However, this is not, you cannot compute this because you don't have P theta Z given X. If you had it, then why would you even bother, right? It turns out in very few lines of math, you can actually turn this objective into equivalent objective of maximizing the evidence lower bound, which is defined with this expression. It's an expectation over your approximate posterior of this ratio. The numerator is actually the joint distribution, P of x given z times P of z, divided by the approximate posterior. And it turns out exactly, if you maximize elbow, you're going to exactly minimize this KL. And by the way, this is the elbow. So here's like a little piece of like information. So in our group, some of us are interested in this theory called free energy principle. It's a neuroscience theory, and it turns out there is exact relationship between elbow and machine learning and free energy in neuroscience. So if you want to remember this, just remember this image. Elbow is negative friston, or no? Okay. But why online inference? So this is where it gets really interesting. It turns out, there's no such thing as static inference, because the real world is that there's no images in the real world. There's a video. When you go out there and live your life, there's constantly evolving visual stimuli that you receive, and you have to just keep updating your posterior in real time. That's the idea here. Like if you have a different sequence of images or let's say frames in video trajectory number 1, and you have trajectory number 2, these are going to lead to different priors. And if you even have the same likelihood given from the same exact frame, you're going to have different posteriors or different perceptions. And that motivates us to move from static inference to online inference, where the key difference is that in online inference, the prior itself is evolving in time. So you just constantly receive new information and update your prior as you receive more and more information. And we just actually were talking about this with like our reviewer, so that like I have two very readily available examples to share with you. This is known as serial dependence. This is a neuroscience phenomenon where people have observed that human perception is strongly dependent on the recent history of stimuli that you have seen. So you can actually just make me see different things if you prompt me kind of with different visual stimuli. And another high-level cognitive thing is that the notion of learned helplessness. Like if you keep failing and you're going to update your prior in real life, that's, I failed, therefore I'm a failure. And that's kind of like a learned helplessness. Where you can also model as online Bayesian inference. And by the way, it goes the other way too, right? So you can say, I got lucky, I must be a genius. Which is totally not about VCs. This is a joke. Yeah, we're not talking. Okay. Okay. So online inference is the only inference that exists in the real world. That's the point. That static inference does not exist. That's it. We've done. Now we're going to talk about BONG, because BONG gives us exactly 80 different types of algorithms you can derive for online inference. It's a massive paper. But yeah, we have to understand this other massive paper, BLR, to understand BONG. So let's do that first. And here are just some quotes reproduced verbatim from the paper, the BONG paper. BONG can be seen as a special case of BLR with one update step per observation, learning rate 1. We'll see what this means, but it's just so you know, BONG is a special case of BLR. In another place in the paper, they say BLR is a mature theory, including several clever tricks we have not yet incorporated in our framework. So it's like BLR is just massive. It's like a great paper. And this is kind of this is what you might think BLR is about at first. Like, new algorithm is discovered, it works surprisingly well, people explore its properties, and then Bayesians come out and say, oh, actually, this is just Bayesian inference. And BLR does that. They're just saying like, look, all of these well-known familiar algorithms like SGD and whatever, Adam, dropout, they can be derived from Bayesian inference. Which is not true. You'll see it down the line. This is not what they do. They also use this framework to derive new algorithms from top down. That's why it's cool. But just so you know, like this, I recently learned this is called base planning. So it's like, just so you know. Okay, let's talk about VLR. So the core contribution is that many familiar learning rules are instances of this thing they call VLR. This is the abstract. So the key idea is that deriving such algorithms to approximate, so they just have like different approximate posterior candidates with different approximations to natural gradients, gives you different algorithms. We're going to try to understand what that means in a second. All right, so our starting point is equation 2, which is, you can call this generalized variational inference. But so if this guy here, there's this loss function, y and x are your data, f theta is your neural network, and this is whatever loss you have for your neural network, and there's an expectation over q, and then there's the KL, right? This looks a lot like the elbow that we just derived or showed you in the previous slides. This is not elbow exactly because this loss function is just a generic function. If this was a log likelihood, if you had a precisely defined likelihood function, and then the log of that would be this function, then you would have exactly elbow. You would have exact variational inference. Because this is not in all cases the log of a likelihood function, it's called generalized variational inference. And then whatever you optimize, the approximate posterior Q that you optimize to maximize or minimize this thing, this negative elbow, actually free energy. If you minimize this and find this Q star, it's called generalized posterior.
I have a question about, so in general, like a lot of times people replace the likelihood in machine learning papers with just like a loss. Pixel reconstruction, and like that. That then falls in this category here?
Absolutely. If you have this KL, yes.
Yeah, okay. So basically, you can call it generalized variational inference whenever you have a loss function and you put a KL on it.
Exactly, yeah. You can even make LLMs like the next token prediction, make it look like Bayesian inference if you just do this. Yeah. In that case, you even have an exact likelihood because it's just, it's a log of the cross entropy. But yeah.
As a matter of fact, RLHF for LLMs is literally this.
What is the KL there? Between what and what?
Between the posterior RLHF trained LLM as the Q and the unsupervised pre-trained LLM as the P, as the prior.
Okay. So you don't want to deviate too much, but you want to, okay, cool.
And so just to clarify, so is the main difference here is that it's just a non-normalized log likelihood, like it's just not normalized.
It's not a log of a density, that's it, yeah.
But you could like still do like e to the power of that and get the energy function, energy function. So the only difference is it's not normalized.
I guess, yeah, probably, yeah. I think that's usually the problem, right? The partition function. I don't know the details. This is kind of a ongoing research, like what is generalized VI. There's another paper from 2022 where they substantiate this idea. But yeah, I think that might be it. Yeah.
I guess one of the questions, like, what if you just replace it with an arbitrary likelihood? Are you still making a particular variational assumption?
No, that's not a variational assumption. Only assumption in the variational part comes from choosing the family of candidate distributions.
For the posterior.
For posterior, yeah.
Very. So it just determines how you're sampling from.
Yeah, exactly. I mean, I guess in order to set up, it's a good point maybe to mention this, that if you want to do variational inference in an online setting, you really have to make two important choices. One is what is your posterior approximate posterior family, which you also make in normal variational inference. But then you don't have to make a choice for prior, because that's just like the prior is the next posterior, right? And then of course, the likelihood is always a separate distinction, like a separate and distinct choice you have to make from the variational posterior. Yeah.
And is the likelihood is the likelihood guaranteed to be like amenable to whatever variational family you have? Because
okay, maybe you're talking about the conjugate case. Yeah. Well, we have that. Yeah. So that's a very important point, actually.
Yeah.
So the key point, actually, one of the beautiful things about variational inference is that you're not limited with that. Just go wild with your choices. You can choose anything as long as you can minimize the you can find optimal parameters. Just choose anything you want.
But is that existence guaranteed?
Existence of what?
Of optimal parameters.
I don't think I can say for in general guaranteed. Maybe there are like people with like theorems that like what are the requirements for this to exist or something.
Sorry,
Yeah, go ahead.
what do you mean existence of the variational parameters?
The optimal ones.
Ah,
So,
so
like,
by
for example-
construction, there always, within any given variational family, there always exists, some global optimum or, at least
Are you
one
sure about
global
the global
optimum.
part? I think the point is, I mean, of course, there exist local ones because
Yeah,
it's trivial, right? I think Thelonious' question is if there's a unique global optimum, which I don't know
It's
about.
not necessarily unique.
Yeah, usually like this also potentially relates to questions of like identifiability. Like sometimes if there's like an infinite family of or like a manifold of parameters that are have equal elbow,
Yeah.
but they're very distinct final posteriors. So that's like a problem with it's a degeneracy problem.
Yeah, exactly.
Yeah.
I guess the question is like, if you choose it, the correct likelihoods and formulations, then you can get in the conjugate situation an actual
Exactly.
like,
In
convection.
the conjugate situation, you probably don't even need to do this because you probably can just compute the posterior, which is what they do in BONG. Yeah. Okay, so the starting part of BLR is generalized variational inference. What's comes next is component one, of course, is pick an approximate posterior. And in the paper, they have a general exponential family form for the approximate posterior. So just to familiarize ourselves with the actual, like lambda here is the variational parameters. Theta are latent variables, and in BONG, they're going to be just neural network parameters. But if you're doing variational autoencoder type of inference, then you could have like theta be your latent variables, but that's just a minor detail. So what's important is that lambda are the variational parameters, and if you express that in this very kind of canonical format, lambda is also called natural parameters, which is what we have here. So lambda are natural or canonical parameters that are multiplied in this kind of inner product kind of way to sufficient statistics, T, and then A is the log partition function. So this is kind of like the standard textbook exponential family definition. So that their starting point for the approximate posterior, and they say that examples later will include multivariate normal distribution and the Bernoulli distribution for Q. So they actually narrow it down later.
Are these exponential families like broad enough to encompass like I think a common assumption I've seen is that any distribution that is out there is close enough to an exponential family distribution that you can describe it. But and then you carry over the nice properties of like just the existence of sufficient statistics and stuff like that. But I'm not familiar with the statistical mechanics. I'm curious, like how can you just arbitrarily increase the number of statistics until it's
it's not about increase, like T theta could be a complicated function of theta. As long as you just say like it has sufficient information to actually just fully determine your parameter, that's the kind of conditional independence assumption. So you can actually make T theta. Yes, go ahead, if you like.
So exponential families are the maximum likelihood families, or sorry, not likelihood, my mistake, maximum entropy families for the moments specified by their sufficient statistics and natural parameters. So for instance, in a Gaussian, if you know the first two moments, that is the mean and the variance of the distribution, then a Gaussian is the maximum entropy distribution with that mean and variance.
Eli, do you mean expectation parameter when you say like the sufficient? Is this what you were referring to or no?
I'm referring to, no, not the expectation parameter, the mean of the distribution.
Okay. And if you have the mean and variance and you plug that into maximum entropy formula, it gives you back Gaussian.
Does the maximum entropy depend on the support though? Of the distribution?
Yes.
Yeah, because these are all for, like, Gaussian is only in the case of unbounded support. So if you're inferring like phase, for example, you're on the circle now, and the maximum entropy is just uniform. In fact, over any.
But depends on what statistic you want to constrain. So maximum entropy idea comes from Jaynes, where he recognized probabilities are subjective. And he wanted to say that, look, if you know such and such properties about your system, and you want to make sure that the distribution you construct reproduces those properties because that's your knowledge of the system, then you, like, let's say, I know that the mean is this and the variance is this. Those are my knowledge. Put those there and then say, like, this is my support also, that's also your knowledge. And then maximum entropy gives you the distribution. And in your case, if you have additional knowledge, like in unit circle, it might deviate from uniform if you put those in your formula. So it depends on what you want to actually put as your knowledge.
You mean deviate from normal?
No, like I'm talking about the uniform distribution, which is maximum entropy, I think, for
any closed
circle or something. Yeah. Yeah. But it's not necessarily always.
Maybe we're getting a little distracted here.
Oh, yeah. Anyway, so I think this is.
To add something quickly as well. So I think, and especially because of that, this has gotten a little bit abstract. So just to bring this back to BONG quickly, which we'll be returning to in a couple minutes, but to make this really concrete, the what Q here is defining is a distribution over possible parameters for the deep neural network. So given that we've seen a certain number of data samples, so in this case, it's a supervised setting. So it's going to be inputs X and labels Y. This is a distribution over possible parameters of our deep neural network that we think could do a good job of classifying the data we've seen so far, just to make sure everyone's on the same page about that.
That's a very, very good point. In BONG, the sufficient statistic is going to be given to us by the neural network that actually takes the input X and has parameters theta and produces some output, which is the sufficient statistic. So it's a very, I think, great point. Let's move on. Next component, so that you chose your approximate posterior, what do you do with it? You apply this optimizing algorithm, which they call Bayesian learning rule. It's just saying, like, look, just optimize that, generalized variational inference, whatever, generalized elbow using natural gradients, which is defined here. So this gradient with a tilde on it is the natural gradient of an expectation, which is just the Fisher information matrix, F inverse times the normal gradient of the expectation. This is the definition of natural gradient. And they put this in their prescription for a very good reason, which is the point of the next slide. But if you have any questions on this, let's talk about that before I move on.
I have a maybe simple question. So there are two things that we're picking. We're picking both some distribution and then we're picking a distribution to parameterize the original thing. If we pick, say we're doing neural networks and we pick some distribution to pick the model weights.
In BONG, we do that. In VLR, it's more general.
Right, but you're picking the two things, right? You're picking the thing you're parameterizing and then you're picking the thing to generate it. Right?
Exactly, yeah. I think so, but I just want to highlight that it's not important. It's not the central thing in VLR. It is in BONG.
Okay.
The other choice of how do you construct your sufficient statistic is a neural network aspect, which is not central to BLR, but is for both. So let's talk about natural gradients, which is a very important but often overlooked component. So this is from another paper from Khan, the first author of BLR from 2018 or something, tries to give us an intuitive way to understand why natural gradients are the right thing to do when you're optimizing in the space of probability distributions. Let's focus on the first figure here. So there are two Gaussians with mean 1 and 10. Actually, it should say 0 and 10, I think, right? And the variances are equal here. And in this case, they have Euclidean distance, like the mean parameters have Euclidean distance 10, because this is mean 0, this is mean 10. And the variance doesn't matter because in Euclidean distance, there's no such thing as Fisher preconditioning. But then let's look at these other distributions. They have the exact same means, 0 and 10, but larger variance. They have the same Euclidean distance, but it just doesn't feel right. Let's just look at this. I mean, it seems like these guys should be more farther apart than these guys because, there's some sort of they're more overlapping. And you can account for that by using natural gradients, which is defined like this. So if you have a loss, and lambda here are your variational parameters, it is for Gaussian, it is the mean and the variance. So imagine just lambda is just the mean. So, and your loss depends on mean, lambda. And the gradient, this is the normal gradient of the loss. If you just multiply it with this Fisher information matrix or inverse of it, you're going to get the definition of a natural gradient.
So what's the hat definition?
The hat, I don't know about that. I think it's about like some estimators. Like in that paper, they were talking about like, you're estimating the gradient rather than being like exact or something.
As stochastic estimate.
I think so, yeah. But that doesn't matter. Like imagine that doesn't even exist. So this is key. Like if you precondition your gradients with the Fisher information matrix, it becomes aware of the geometry of the space of distribution. So they're gonna these two guys are gonna have now different distances. And the general rule of thumb is that you use Fisher preconditioning whenever you have a closed form for you can compute this thing in closed form, which you can do if you have like some simple distribution like Gaussian or Poisson in our case. But there's some caveats. If you really have like a big neural network, then it's really hard to compute this Fisher information matrix because there's a memory cost. There's also a time cost. It's like if K is the dimensionality of your latent space, then Fisher information matrix can be costly to compute. Therefore, there's like a trade-off. You might be better off just using Atom in this case, like if you have like a big neural network. Oh. Now let's go summarize. If you pick an approximate posterior, apply BLR to optimize the variational parameters, you're going to get a new algorithm based on whatever choice you made. That's the whole point of BLR. And this is just a quote reproduced from the paper. Different exponential families Q, the approximate posteriors, give rise to different algorithms. And within those, various approximations to the natural gradients that are needed sometimes give rise to many variants of those algorithms within that family. That's the whole point of BLR. And if you apply that prescription, you end up deriving all sorts of very different, seemingly different algorithms that are listed on the left-hand side in these three different groups, like optimization algorithms, deep learning algorithms, approximate inference algorithms. And then here are the list of choices you have to make for approximate posterior and the natural gradient approximation. And what I want to highlight here is that, of course, some of these are just well-known algorithms like RMS prop, Adam, dropout, whatever, Newton's method. However, there's these little things in parentheses, new. Let's look at those. These are new algorithms that the authors of BLR apply. They apply their framework and derive these algorithms from a top-down manner. Therefore, this is not true. This is only half of the picture. BLR goes beyond base explaining. It actually derives novel algorithms. That's why it's beautiful.
Do the novel algorithms make better than me?
Good question. I don't know. I hope so. But I think in the paper they mentioned like why they're, if it didn't do anything better, they wouldn't put it there. That's my guess. Or my hope.
So what's with this none in the in the natural gradient approximation column?
I guess you don't need to do it. I don't know. This is something that I didn't understand. Like, for example, when you have a Gaussian, for your approximate posterior, why do you even need to approximate that natural gradient? What does it mean? I don't know what delta method is. Like, these are just like some of the details of the paper that I'm not familiar with.
That one says fixed covariance, but actually no, but then it says the same for the Gaussian and
Oh, yeah.
I'm not sure what
So we are more familiar with like what happens in BONG. So maybe we should talk about this point when we get to the BONG discussion.
There's also a question in the chat about when you were talking about the natural gradient methods, what paper were you drawing on?
I can drop it on Slack. It's Hahn and Nielsen 2018. All right, so let's talk about BONG. Finally, we get to the actual paper after 1 hour. So okay, it's a special case of BLR, as we saw, and it narrows things down in the following ways. First of all, it doesn't do iterative many natural gradient steps per data point. It does one single gradient step per data sample with learning rate 1. And here are the equations that are important. This is equation 1. BONG starts with this. This is just literally, negative elbow or free energy. Here, D are your data. Theta are your neural network parameters that you want to perform inference over. Q, psi are your approximate posterior. Psi are the variational parameters, and so on. This is just a normal elbow. However, when you take this normal elbow and go to sequences, there's like a time thing. You end up with this equation where psi is now a function of time. It's online inference. It's evolving in time. You don't have a fixed posterior, it's evolving in time. And X is, let's say, MNIST digits, and Y are the classification labels, which is the case in BONG, but it could be anything, like it doesn't matter. And theta are neural network parameters. And now we have this KL between your current posterior and this entity here, which they call prior predictive distribution, but you can just think of it as prior. And what happens
is the prior given all of the observations you made up to that point?
Up to that point, but there's a little catch here, which we're going to get to that. If you have, yeah, exactly, that prior kind of captures and kind of summarizes, abstracts away whatever you've seen so far, right? But it's also related to the posterior from previous time step. It could be exactly the same, that posterior, but it could be a function of that, which is what we're going to talk about. But yeah, let's think of it as a prior. And what happens if you do these things, like single gradient step with learning rate 1 is actually the KL drops. That's very interesting. We're going to talk about that in some detail. So if you apply the BLR iterative update rule with like the Fisher preconditioning, whatever, you end up getting this very interesting result where you see like the full loss had both a log likelihood expectation term and a KL term. But it dropped here in equation 3. Where did it go? We're going to motivate that in the next slide, which is one of the key contributions that the BONG claims. They talk about it here. They're saying that because in the first iteration, in BLR's first iteration, this guy vanishes. The gradient of the KL term vanishes. Therefore, BONG can be seen as a special case of BLR, whatever, which we talked about. And their contribution is to recognize that doing the single update step allows the KL term to be dropped entirely. Which I'm not sure if this is like this required a second sentence to say. It's just like it's a mathematical mandate of that the KL drops if you do one iteration. So I guess their contribution really here is that they're saying like, let's just do one iteration. It's good enough, both theoretically and empirically. And it also is convenient because the KL drops, so you don't have to compute the KL.
Are you going to go through that derivation?
Yeah, I'm going to show it. Okay, but I can actually just give you the intuition. So the KL divergence is a differentiable function with a global minimum of 0. Because it's differentiable and because the global minimum happens at 0, then the first derivative also vanishes at 0. That's the whole point. That's it. That was the derivation. So we just derived this equation, but I'm going to show you explicitly why that happens, let's say for Gaussians, because that's what BONG does. BONG has only Gaussian variational distributions. If you write it out explicitly like this, this is the posterior, this is the prior, and these are the parameters associated with the mean and the covariance of the prior and the posterior. Looks complicated, but actually it's not really that complicated. And then now let's compute the derivative of this thing with respect to both mu and the covariance, because those are our size.
So what is this K just a constant of integration? Or?
No, it's just a dimensionality of real latent space, which actually I should have used P because in the paper they use P, but K is the number of latents you have, let's say, the size of the vector, your variational parameter vector. Okay. I'm sorry, like the variational parameter is just like both mu and sigma, and it's the dimensionality of mu, let's say.
Sorry, and then one more question is just the last long term there.
Yeah.
Are in the bars, is that supposed to be like the operator norm?
It's determinant.
Determinant,
Yeah.
okay.
Yeah. So if you take this expression and compute the gradient with respect to mu, the first variational parameter, you end up with this expression. And you notice that if you put mu t, if you initialize mu t at the prior value, this vanishes. So we get that, check. And then you do the same thing for the covariance, and again, it vanishes. So both theoretically and in this concrete example, we see that the gradient, the first derivative of the KL vanishes if you have one iteration. And that's why BONG can, get away with dropping the KL term entirely. So just to summarize so far, they say, let's start the BLR, but only do a single gradient step at learning rate 1, and the KL term drops. That's the summary so far. There are 2 or 3 more narrowing down happens in going from BLR to BONG. The variational distribution is Gaussian, even though in BLR it was the full exponential family. The likelihood is now we have an exponential family for the likelihood. And finally, the transition probability is a Dirac delta. It's a little kind of a detail, but it's important because this relates to BONG, the follow-up paper. So the transition probability says, by the way, this is a typo in the paper. It's if you have non-stationary inputs, you might want to actually evolve your latence after each iteration update from going from theta at t-1 to theta at t. But if you just choose delta, you don't really do that update in between these updates, then you have a transition probability that is a Dirac delta. That's kind of the only reason we mentioned this here is because it relates to BONG. That's what they relax this assumption and they explore all possible
dynamical system.
Exactly. But we shouldn't worry about point number 4. We're going to worry about that in September.
Sorry, for the likelihood being an exponential family, what exactly, the likelihood is also a distribution?
The likelihood is a distribution. It's an exponential family, and you have I forgot to put the form here, but yeah, you have exactly the same form. There's a natural parameter times a sufficient statistic minus the log partition and so on.
But it's not normalized, I take it?
It is normalized. It is a normalized distribution.
Sorry, I was zoning out for a second here.
Yeah.
The KL only vanishes because of this transition probability?
No.
No, it vanishes no matter what, because
no matter what.
One step.
Exactly.
And it has to do with basically from that starting point of your prior.
Yes.
Yes, your derivative is 0.
Yes.
Okay.
Because when you have you're currently at your prior, you want to go to the posterior. When you want to do one iteration to go there, if you just expand that equation, you're going to end up here psi t given t-1 plus this thing. And if I had imagine I had plus gradient of the KL, that gradient of the KL vanishes because you're already at your prior and you haven't moved away from it.
Right.
After only one, if you do one iteration, you're going to move away from it, and the KL is going to validate.
At that point,
that's it.
So it's topological.
Exactly.
Right? You do one step.
Yeah.
Awesome.
It's a mandate.
Yeah.
Cool. All right.
Dogma.
And that's the contribution one.
Yeah.
2 contributions.
Yeah, but contribution 2 takes 50 pages to write. Because and it's actually very important because it's going to be clear why we needed additional 50 pages in this particular example of a conjugate case. So
can we go back just really quickly?
Yeah.
So for the question about the likelihood being an exponential family.
Mm-hmm.
So there are 2 different distributions we're talking about here. One is the distribution over the posterior parameters. And then the other is that we're saying that whatever our algorithm is, it's actually going to be outputting a distribution as well. And so in the case of a deep neural network, for example, if you're doing a classification task, you might be outputting a distribution over possible labels. And that would be that distribution.
Oh, and that's the likelihood of that. Okay.
Yeah, exactly. And that's likelihood, and that's what needs to be exponential.
And so that's the element-wise likelihood of the.
Yeah.
Okay.
Or if you're doing reconstruction, you choose whatever, if it's Gaussian, you get MSE and
Okay.
So that's that part. Yeah.
There's also a question in the chat about what's the role of using a learning rate of 1 in dropping the KL term?
That's a very interesting point. So maybe that is a very good point. So the learning rate one does not imply that KL drops. So the KL drops actually is just implied with this part. The learning rate of one is going to be relevant in the conjugate case where we derive exact Bayes. If we didn't have learning rate one, we wouldn't get exact Bayesian update with the conjugate case. So these are separate points. Thank you for that point.
So it's sort of, it's justified, this choice is justified by the special case.
Yeah, they just wanted to have a nice proposition 4.1. So, okay. But, you know, the immediate question that comes to mind is like, is this, one of my friend, like Utkarsh once said, is this kosher from a Bayesian perspective? And this proposition addresses that question. So let's just go over their assumptions. First of all, okay, the observation distribution likelihood is an exponential family with natural parameters theta. So let's look at that. That's equation 6. You have P of data labels y given your neural network parameters is the exponential family. And importantly, you see that the natural parameter is theta, and it's a huge, very, very big oversimplification because in general, this is going to be a neural network. So imagine like instead of having a neural network with parameters theta that accepts some input x and outputs some vector that you use as your natural parameters, just skip the whole thing and just say like my natural parameters are theta t, which even doesn't depend on x. Like it's just a very, very highly artificial setup. So I want to emphasize like how big of an oversimplification this is in order to get this work. So you make that choice, and then you choose this other simple thing for your sufficient statistic for the likelihood. And of course, A is the log partition, doesn't matter. But once you make those significant choices for your likelihood, and if you want to be conjugate, then it kind of really narrows it down for your prior. And just to define conjugate, here's like in Bayesian inference, if you have a prior that has a certain family, and then a likelihood that is like some other family, if you multiply them and you don't change the family of your prior, like you end up with a posterior that is exactly the same family as your prior, you can say that these are conjugate. So like Gaussians, like if you have like Gaussians for both, you're going to end up with a Gaussian for posterior, or like I think Bernoulli and beta distribution are also conjugates and things like that. Anyway, when you choose your likelihood like this, it forces you to choose a prior to be in this form, where the sufficient statistic are like highly constrained, like it's theta and minus a. It just comes from like, multiplying these two things together and like manipulating some terms and end up like with this choice for your sufficient statistic of the prior. Then this becomes conjugate, and you can compute exactly what the posterior is.
Didn't you have to know the log partition function?
I'm not sure. I mean, I don't remember.
Puts it in the vector there.
Yeah. I don't know if you have to know, like maybe it just works for any log partitions. And also, I guess if you have this particular format, you can just compute what just compute the integral and see what the log partition is. I don't know.
Okay.
But the point here is that once you have these choices, 6 and 7, you have two things you can do with this. Thing number one is, okay, you multiply them, you compute the exact posterior. That is the Bayes way. You have that here now. It's like a very awesome thing to have. You do that, you compute the next posterior, and then you save that. And then you forget that you could do that. You just say like, okay, I'm going to actually take these and I'm going to apply the BONG rule on these and then compute the updated posterior using BONG rule. It turns out those two different things give you exactly the same outcome. That's what they mean here when they say like BONG recovers exact Bayes, the conjugate case. And you can actually see the appendix C. It's not a huge derivation. It's just moving some terms around. But yeah, if you have these specific variational parameters, both Bayesian update and BONG yield the following update. They also provide intuition why this happens. But yeah, just to summarize this slide is that if you make these extremely simplifying choices and have a conjugate case, BONG it turns out, is kosher in a Bayesian sense. But now this actually is great because it motivates the rest of the 50 pages of the paper is that the natural parameter is not just some theta, it's actually a deep neural network. So you can't do this. What do you do? Instead is you use these well-known theorems from like 60s or 70s, and you end up with these equations. So the key challenge, the contribution number 2 of BONG is that how do you compute this expectation? You have an expectation, then you have to compute the gradient of that expectation with respect to the variational parameters. Sorry, this should be like psi. Lambda is for BLR, but yeah. You have these psi parameters, variational parameters, and the gradient of the expectation with respect to those. What happens if you apply these theorems that are only true for Gaussians? You end up with the derivative of the whatever that's inside with respect to neural net parameters theta. So you start from this equation 3, you end up with equation 9 and 10. So you get to update your mu and sigma using these rules. And this is now complicated because look, you have the Jacobian of your log likelihood, which is roughly like the Jacobian of the neural network, which is a huge thing. And even worse, you have the Hessian of a neural network. And even worse, it's an expectation. What do you do with this? Like, it's like a huge problem. And there's all sorts of things you can do. You can do approximations, and you can do Monte Carlo, approximation, whatever. We're going to talk about those. That's what Kaylene is going to present to us. So go ahead.
Yeah, so I guess the rest of the paper is defining, like Hadi mentioned earlier, about 80 different algorithms, plus or minus a couple, based on the combination of 2 main factors. And so the first factor is going to be the update rule, where all of the material that Hadi was just introducing gives us the one in this lower right corner here, which is the Bayesian online natural gradient. And so the 2 key ingredients for this is that we are only doing 1 posterior update for each new data sample that we take in. And then for the gradient that we do in response to this, we're going to use the natural gradient instead of the regular gradient. But you can also define what the algorithms would look like in the other 3 quadrants in this setup. And so in the multiple steps, of course, we have the Bayesian learning rule, or at least the narrower version of it, where we use the Gaussian posterior distribution and the exponential likelihood. And then for these top 2 rows here, there's also been a previous proposed work that was called Bayes by Backprop that did the regular gradient for multiple updates. And then not in prior work, but also defined as kind of an ablation algorithm in this paper is the Bayesian online gradient, which is exactly the same as BONG, but does the regular gradient instead of the natural gradient. And then as Hadi was saying again, in order to actually get an estimate for any of these update rules, we need to be able to get these estimates of the gradient and also the Hessian because of this price-Bonnet rule. And so the second main decision point that the paper introduces is different ways to approximate this second order information that we need, which can be kind of gnarly to compute. And so the main 2 axes that we have here are whether we're going to do a Monte Carlo approximation or whether we're going to try to linearize, in this case, the deep neural network, so linearize about the parameters to try and get a more tractable estimate. And then the other thing they consider doing is instead of using the Hessian, you can try to use the empirical Fisher matrix instead as an approximation to the Hessian, which is going to be much, much more tractable to compute. And again, you can sort of combine these 2 factors in any way you want to get 4 different approximations that you can use for any of the 4 update rules. So I guess, yeah, that this is how we get to a lot of different algorithms. So just to go through quickly, we don't want to go into these different estimators into too much detail, but just to give you a flavor of what's going on here. So the first and simplest to understand is in this upper left corner, which is where we're going to use the Hessian itself and just use a Monte Carlo approximation. So what this is going to look like is we just take the gradient of the loss and then also the Hessian of the loss at particular samples that we estimate. And then we're just going to take the empirical mean of these 2 quantities to get our final estimates for these 2 things. Some caveats is that taking the Hessian of the loss is not as bad as taking the Hessian of like the whole deep neural network, but it's still pretty expensive, especially for larger models. And empirically, they find that the performance of this is actually like terrible. And so they don't even really bother to show it in the plots because it's just awful compared to everything else they tried.
So the monocolor is just for the excitation over your posterior?
Yes. Okay, so then in order to make some improvements to this, the next thing they try is to replace that Hessian estimate with the empirical Fisher approximation, which requires this thing right here. And so they get the same gradient as before, but now with this much nicer estimate for the Hessian, which is also just based on this empirical gradient that you get. So some caveats for this is that you still need to take a bunch of Monte Carlo samples, which can still be slow. And this number of samples that you take is going to determine both how fast the algorithm is and also how accurate it is. And so this is like a kind of a hyperparameter that you need to tune, which could be, something that is not necessarily so nice if you're just trying to get something running quickly. And actually, they find that empirical performance for basically like you can increase the number of samples of M such that this is actually slower than the next two methods I'm going to talk about. And even so, the empirical performance is worse than the other two methods. So again, it doesn't really seem like there's a great reason to use this kind of method. So then what they do is they propose trying to do a linearization of the deep neural network to get a more tractable and faster to compute estimate. And the definitions for this go back to what we were talking about earlier, where the deep neural network is assumed to be outputting something in an exponential family. And so they define some quantities related to that property that we're not going to get into too much here. But the takeaway from this is that by doing this linearization, we we can use the exact estimate of the Hessian without needing to do the Monte Carlo samples, which is really nice. However, computing this quantity does still require taking the Jacobian of the deep neural network, which again is like computationally has some caveats there. And so this motivates the final method that they talk about, which is the same as the previous one, except now we're again going to use the empirical Fisher instead of the Hessian. And when you do that, you no longer even need to take the Jacobian with respect to the neural network parameters. And so this gives you a method that is quite fast. And actually in the experiments, as I'll show in a second, it seems like these approximations, while maybe not super well justified theoretically, seem to produce really good estimation of the quantity we're after in practice. So, so speaking of experiments, we can just talk about these briefly as well. So the way that the experiments are set up in this paper is that we are going to try to take in individual samples and labels on MNIST, which most of you are probably familiar with, but it's just a data set of these little images, grayscale images of handwritten numbers. And the goal is to classify which digit is shown in each image. And so we're going to get individual samples, examples of these drawn from the entire training distribution. And we're going to update the parameters of a small convolutional neural network using this approximation to the Bayesian online natural gradient to move towards getting a better classification on this problem. So by doing this, we're going to get these kind of plots where on the x-axis we'll have the number of training samples. So we're looking at a data efficiency metric here. And then on the y-axis, we're going to be looking at how good of a job our current best estimate of the parameters is at classifying the examples in the test set on MNIST. So just quickly, based on the motivation that Hadi was talking about earlier, I just want to take the temperature of the room. Like, how do we feel about this task as a nice example of doing online learning? Any thoughts?
Pretty simple.
Yeah.
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 I don't know. I mean, I think what really broke MNIST's reputation for me was that I saw maybe I can send a reference that like most MNIST digits can be distinguished by a single pixel, like pairwise.
Really? Oh, wow, which pixel is it?
Interesting.
That's amazing.
What is sample efficient by order of magnitude? What are we talking about in terms of state of the art?
That's a good question. They don't have any baselines outside of this Bayesian setting. And I was quite curious how this compares to like all possible algorithms, and I wasn't able to find something quickly. So, but I think that would be a really interesting baseline to have.
One of the main benefits of doing like Bayesian is that it's sample efficient, right?
Yeah, so I guess this would be a question for the room, but if we were doing the exact perfect Bayesian update, it shouldn't be possible to do anything better than that if the prior is good, right?
I mean, depends on all the other choices you make, and I don't exactly know how they implemented this thing, and if there's any other regularization or like other things they do during training.
Yeah.
Usually these things end up like matter more than we would like them to matter. So I guess that's a problem. But yeah, maybe like Kaylene's point here is that like, online, is this really online? It's not, right? So, but maybe like to give them like a little like the benefit of the doubt is that in this paper they don't have any transition probability. So in a true online non-stationary case, you would have some evolving dynamics in addition to whatever they had. So I guess this was just they wanted to have some experiments to show that it works, right? I don't want to like I personally don't care or like I don't really take the experimental results very seriously. But maybe like we could just go through them, like.
Can you just actually just clarify for me? Is this online in any sense? It sort of seems like this is identical to doing supervised learning.
Yes.
With like a batch size of one.
And that's exactly the point that I was, So I think not only is this not stationary in the sense that, not only is this stationary in the sense that we're assuming that the underlying like problem we're trying to solve is stationary. There's nothing that's changing about MNIST, but actually we're also assuming that the training samples that we're getting are IID.
Yeah.
So this is really like, we're just solving the standard supervised learning problem and just showing that we get good sample efficiency. Yeah.
Yep.
Yep. And this is just reiterating what I was hoping to get at with that. So, all of this stuff that we just went through makes really way more sense in a setting where we're actually doing online adaptation. And the main caveat from these experiments is that we're not really measuring or looking at online adaptation. And just to reiterate, the reason that all of this stuff makes way more sense in the setting is that, for one thing, the prior that we've learned from previous data is actually meaningful. It's not just some like unit Gaussian. Sample efficiency is highly desirable if we're trying to do adaptation because we might not have that much data to work with when we're trying to make good decisions. And, if we actually do have non-stationarity, then we can actually make principled adaptation as the data is changing in real time. And that's exactly what we're going to discuss in the next journal club with BONG, which explicitly considers this setting. With all that being said, here are some of the plots that we have that are talking about performance on MNIST. And so the kind of overwhelming number of different things here is just a small fraction of the number of combinations of algorithms you can get by combining. So these first 3 or 4 letters here is the update rule. So BONG, of course, is the one we're most interested in here. And then this last part of the caption is going to be which of the gradient estimators they used. And then the takeaway from this plot is that the best performers are actually all of these approaches that have the single iteration per new observation. And so really the key takeaway here is that we're not losing anything by only doing one iteration per observation and getting rid of the KL term and all of that nice stuff. And then also that these linear approximations, the linear, both with the Hessian and with the empirical Fisher, are doing a really good job at getting a lower misclassification rate very quickly on the scale of a few hundred of training samples. And then they also have one other data set that they put in the appendix, which is this Sarcos regression data set, which is kind of a fun setting where you're getting, it's like a robotics inspired problem where you have to take in the joint angles and I believe the torques for the joints, and then you have to output the acceleration of a chosen joint, or I might have it flipped where it's you take in the acceleration and output the torque. But either way, it's kind of a fun little problem for that. And the main takeaway from these plots is that, so this is just more directly drilling in on these 4 different update rules. And what you can see here is that this plot on the left is forcing all of these update rules to only use a single iteration. And the ones that are doing best here are the BONG and BLR. And so that kind of makes sense that they would be basically the same in the one iteration case. But then if you look over here, if you then put BLR to 10 iterations, you can see it's really not improving that much. And so again, this is just iterating that the extra iterations in BLR don't actually seem to be helping much in practice. And then one other small kind of mildly interesting thing here is that the BBB approach, which was the regular gradient and with multiple iterations, actually does seem to be getting closer to the natural gradient methods once it's allowed to have multiple iterations. So in that setting, it does seem like they're helpful, but if you're doing the natural gradient, it seems like you kind of have all the information you need with one iteration. Yeah.
So I'm actually really curious about this. Maybe we can save it for the discussion, but do you have any intuition why this is true for like complicated neural?
Do you think it would be more general than just this example here? Is that something to do with the data or something to do with the?
Yeah, so I guess maybe these are both very simple problems. Maybe two things that might make us feel slightly better about the generalization here is that in MNIST, we were doing a CNN, and here we have a very small MLP. So these are two slightly different architectures. And then also in this setting, we're doing a Gaussian output. So this is a regression problem, whereas in MNIST, it was a classification problem. So we were outputting probability distribution over the class labels. But yeah, I think that's about as far as that goes. These are very, very simple and small problems.
Yeah, if you have a really complicated neural network, then maybe you want to do more iterations. Update or prior. Or do you think always, one step updates is the right way to go?
It's really hard to actually, I don't really have an intuition, but in our own work, I think what really helps us is that, the KL regularizer is sometimes too strong. It just doesn't let you to deviate too much. And we didn't report this in our paper, but I did some like additional inner loop iterations, just experimenting with this. We never got anything from that.
Yeah, I've also run such experiments, but I guess those are like more for like latent with like given like one sample.
Yeah, totally different. Yeah,
it's very different from like a neural network where like it's really
more complicated.
And more complicated with respect to the parameters of the neural network.
Yeah.
Is the empirical Fisher reevaluated every iteration?
It should be, I believe.
I think, yeah, because when you iterate, you update your prior value and wait.
Because the empirical Fisher is like
it's evaluated at the prior. So if you're updating your prior, I don't think you evaluate each iteration.
Would that not be maybe a problem?
Yeah, that's a problem. So I'm basing this on the equation in BONG, but in BLR, they actually have this, it's clear in their equations that the Fisher is always evaluated at the posterior, which is the right thing to do, and which is what we did also. But the BONG equations seem to suggest that it's kind of evaluated at the prior predicted distribution, which actually I don't think that's good. Yeah. So this is a good point to actually clarify. I'll double check after this meeting, but for sure, what I can say with 100% certainty is that it should be evaluated at the posterior because that's where you're currently at.
Yeah.
The local geometry is determined at the point you're at. It doesn't matter where you were 10 steps ago, right?
Especially the more iterations you have, the further you are.
Exactly. Yeah. So that's the part that I'm sure, but I'll double check. So that's a good point.
And am I right in thinking that's probably the most expensive part of an iteration? Or one step?
The problem is you don't really have that problem. If you actually choose a well-behaved distribution like Gaussian or Poisson, that's close to form.
Yeah.
So the Hessian is, in their case, Hessian and Jacobian are the problematic parts, which is just about the neural network. You don't have any close form there.
Right.
So for us or for even for them,
right,
it doesn't matter.
Yeah. And then you might actually, I feel like the one problem also is that as you're iterating the Fisher information is more, it's very likely that it's going to be fairly different at the posterior than the prior.
Depends how much you deviate, but yeah, I mean, the right, that's kind of logical thing to, even if it's not that different, the logical thing to do is the posterior.
Yeah, you might want to do like an inflated Fisher information.
Wait, sorry. So basically, this is help me understand this. I'm taking a step to where I am at my prior. Should I respect the geometry of where I am now or the geometry of where I end up? Is that what this is about?
When I take the next step, you need to